Welcome to 11.5 through the end of chapter 11. We're going to skip heat engines and heat pumps in this chapter, but we are going to talk about the first and second law of thermodynamics. And so in this chapter, we've been talking about energy, and we've talked about conservation of energy and work and power and these kinds of things. And today what we're going to specifically talk about is thermal energy. We've kind of alluded to this all along, and we did talk about it in terms of thermal energy equaling the kinetic friction constant times the distance that you drag something, right, due to friction. So we know that thermal energy can be created, and we've also talked about it being kind of lost to a system, unable to do work. And so we're going to explore these ideas just a little bit more. What I want you to do in your notes is go ahead and make this table with the words heat, thermal energy, temperature, and Boltzmann's constant. And I'd like you to go ahead and write out your definition of just everyday what you think these are, right? And I want you to go ahead and look up in your book the physics definition of these and maybe any equations or variables that you find that go along with them. If you can pause the video here and go ahead and do that, I'm going to go ahead and go on to the physics definitions and the equations of those things. So heat and thermal energy and temperature are again kind of like work and power, things that we use pretty loosely in our language. And so what we need to do is to kind of redefine these in terms of just physics terms so we don't get them confused with how we use these words on a day-to-day basis. All right, so for heat, we're going to use the symbol Q, and heat is a form of kind of changing in energy, and so it's measured in joules, just like work and energy that we've talked about already. So this is measured in joules, J. Heat can be added to a system or taken away from a system, but overall it's kind of like work. It's a way of transferring energy to or from a system. So an energy or a system can do work and lose energy, or you can put work into a system to create a different kind of energy or to transform that work into a different kind of energy. Heat is the same way. I can add heat to a system by, well, heating it, right? And so I just have some fire, which of course is really good at drawing. And I've got a system like a pot of water, and I can add heat to that system. And that heat gives that system a little bit of an energy boost. And so heat is a way of adding energy to a system. Heat always goes from hot to cold, and this is going to be an important thing to note. If I put work into a system, I can make energy go from cold to hot, but very naturally things go from hot to cold. And so the energy from a hot system that comes in contact with the energy of a cold system gets transferred from the hot system to the cold system. Again, we're using Q to represent this idea of heat. If Q is greater than 0, and this will make a little more sense here in a minute when we start talking about equations, but if Q is greater than 0, then heat is being added to a system. And if Q is less than 0 in our equations, then heat is being lost from a system. So like a car radiating heat, or your body after you work out. And then heat being put into a system would be like heating a pot of water, right? Q is greater than 0. All right. So we've got this idea of heat. We've also got this idea of thermal energy, which is also measured in joules, right? This is part of our conservation of energy laws. That energy is never created or destroyed. It's only changed. And this has been our phantom menace so far. When you take calories into your body, you're not able to use all of them for work. Some of them get transferred to thermal energy, and that doesn't really go into you running or playing basketball or whatever. It's just kind of lost out into the universe, and so we're going to explore this more today. Specifically for a gas, the thermal energy of a gaseous system is equal to the total kinetic energy of that system. And this is important because it's the total kinetic energy of all of the molecules in that system. And we're using N as the number of atoms in that system. And so this is kind of interesting because if I have a bigger system with more atoms, right, then the thermal energy goes up. If I decrease the number of atoms included in that system, then thermal energy goes down. And so it's the total thermal energy of a system. And in a gas, this is all really random kinetic energy. Those molecules are just bouncing from place to place. We have these equations over here that thermal energy can equal the number of atoms times the average kinetic energy. Or we can say 3/2 times the number of atoms times this idea of the Boltzmann's constant. And we'll get to that in just a minute. And then the temperature in Kelvin, which we will also get to in a minute. But those are just a couple different ways of calculating thermal energy. Temperature is a little bit different. And temperature is the measure of the average kinetic energy. And so thermal energy was the total kinetic energy. Temperature is just the average kinetic energy for any one molecule in a system. And so technically we can increase the thermal energy by increasing just the number of atoms, right? Not the actual kinetic energy of those atoms. For temperature, if we increase the number of atoms, it doesn't matter because it's just the average kinetic energy of that system as a whole. We measure temperature in Kelvin, which we'll talk about a little bit more in just a second. But the temperature in Kelvin is equal to 2/3 times the average kinetic energy divided by the Boltzmann's constant, which again we'll get to in a minute. And I'm telling you this whole new scale for temperature. Well, what about Celsius and Fahrenheit? Well, it's okay. We can still convert Celsius into Kelvin using that little formula there. And then last but not least, there's the Boltzmann's constant, which is equal to 1.38 times e to the negative 23rd joules per Kelvin. And so when you see this kb plugged in there, that's just the Boltzmann's constant. A really famous guy who did research on gases and temperature and things like this, and so he got to name his own constant. All right, so onward and upward to kind of jump in and learn more about all of these things. All right, so thermal energy. Thermal energy is the total kinetic energy of all atoms in matter, and temperature is just the average kinetic energy of those atoms. And so I've got these two questions that I'd like you to consider, and you can pause the video and do so. But it's what happens to atoms as they're heated? What happens to atoms as they're cooled? And how can I change thermal energy without changing temperature? So let's think about this first. What happens to atoms when they are heated? So we'll pretend that I'm zooming in on a pot of water. And let's actually say that I start that water out as ice, with all of those atoms arranged in a nice neat matrix, and they're all packed in tightly. What begins to happen to those atoms as heat is added to that system? So as I put heat in, what happens to those atoms? And well, those atoms begin to move and they begin to vibrate back and forth. They space out and they gain kinetic energy as I heat them. And so as heat is added, then kinetic energy increases, right? The same is true if I have like some water that I put in an ice tray and it's all flowy and things are moving, and I put that into the freezer and I remove heat from that system, and so heat is flowing out. What happens to those molecules? Well, they begin to slow down and they kind of condense and form this nice neat matrix again. And so when things cool down, we see the kinetic energy decreasing. And then this last question, how can I change thermal energy without changing temperature? Well, we remember from just a second ago that thermal energy, ETH, is equal to the number of atoms times the average kinetic energy of each of those atoms, whereas temperature is just equal to the average kinetic energy. And so I can change thermal energy by increasing the number of atoms that I'm talking about. Increasing in the number of atoms that I'm talking about. And I can increase in to increase thermal energy without ever changing temperature, which is just the average kinetic energy of any one of those molecules. All right. In your day-to-day lives, how do you measure temperature? And I'd like you to pause the video and kind of come up with, okay, well, what's everything you know in your vocabulary about temperature? And you might come up with a few different things, like, oh, I know that I need a thermometer, right, of some sort to measure temperature. And you might say, okay, I know the Fahrenheit scale pretty well, right? And so if I tell you that it's like 20 degrees Fahrenheit outside right now, you know that's pretty cold. And then we also have the Celsius scale, right, which is kind of the SI unit of temperature. And if I tell you that it's 20 degrees Celsius outside right now, you really have no clue what that means, and that's okay. I want to take a second and talk about these two scales. So the Fahrenheit is what you're used to using. Fahrenheit is based off of a really old experiment, but in the Fahrenheit scale, one of the good things to know is that water freezes at 32 degrees Fahrenheit, and you guys are probably pretty aware of that. And then water boils at 212 degrees Fahrenheit. The Celsius scale actually makes a little bit more sense. The Celsius scale is based off of water freezing at 0 degrees Celsius, right? And whew, okay, that's easy. And then it boils at 100, right? And again, those are just nice, easy numbers to work with. It's also important to know that I can convert between these two between these two systems. And I'm gonna, let's see, put those in blue for you. So the temperature in Celsius, right, is equal to 5/9 times the temperature in Fahrenheit minus 32. And the temperature in Fahrenheit, if I'm going from Celsius to Fahrenheit, the temperature in Fahrenheit is equal to 9/5 the temperature in Celsius plus 32. And it's important to note the order of operations here. So if I give you a temperature in Fahrenheit and ask you to convert to Celsius, you'll use this one. And if I give you a temperature in Celsius and ask you to convert to Fahrenheit, you'll use that one. However, the interesting thing here is that I'm not going to ask you to do either as an end result. I don't want your units of temperature in Celsius or Fahrenheit. I want them in Kelvin. Kelvin is a scale such that, let's see, the Celsius scale was such that 0 is the freezing point of water. Kelvin is a scale such that 0 is defined by 0 kinetic energy in the atoms. It's also known as absolute zero. You might have heard of absolute zero before, and you might have heard of the Kelvin scale before, but it's completely based in physics, and so it's, if I have this ice thing happening, the truth is that these molecules still have a little bit of kinetic energy when they are ice. In that water form, they're kind of vibrating back and forth, as are the molecules in all solids. However, we can supercool things to the point that the atoms just barely move at all, and this is the idea of absolute zero. Experimentally, we can't actually reach absolute zero. We can only get pretty close to reaching absolute zero. So anyways, we've got a new scale for temperature that you guys will be using from here on out. So when I use the variable T for temperature, I am always talking about temperature in Kelvin. All right, and so if a problem gives you Celsius, please make sure that you do convert to Kelvin first. This was the Fahrenheit to Celsius conversion. Once you get Celsius, all you have to do is add 273 to convert to Kelvin. And so what is the freezing point of water on the Kelvin scale? Well, that's easy because we know the freezing point of water in Celsius is 0. All we have to do is add 273, and we've got our temperature in Kelvin, which is 0 plus 273 is 273 Kelvin. Please make note there is no such thing as degrees Kelvin. It doesn't exist. We just say Kelvin. So 273. What's the boiling point of water in Kelvin? Well, that's easy too because the Celsius system makes so much sense. I know that water boils at 100 degrees Celsius. All I have to do is add 273 to that, and 373 Kelvin is the temperature at which water boils. All right, so not too bad of a conversion. It's that Fahrenheit to Celsius that's really nasty if you ever have to do it. Usually SI units are just Celsius, and so just add 273 and you'll have your Kelvin for all of your formulas. Okay, so back to this idea of thermal energy and temperature. We said that thermal energy is the total kinetic energy of the system, or we could talk about it in terms of the average kinetic energy if we don't have the number of atoms in a system. And so we'll do 3/2 times the Boltzmann's constant times the temperature in Kelvin. If we do know the number of atoms, right, for an ideal gas, we can plug that in as well, times the Boltzmann constant and the temperature in Kelvin. So let's do a couple of examples. Let's say that I have an ideal gas that's at 10 degrees Celsius. What is its kinetic energy in joules? And so this is what I'm looking for. There's no mention of the number of atoms. And so what I will do is 3/2 times the Boltzmann's constant, which is 1.38 e to the negative 23rd, times the temperature in Kelvin. You've been given a temperature in Celsius, so it's 10 degrees Celsius. And the way that I convert that is I simply add 273. Okay? And once we multiply that out, then you get 5.81 e to the negative 22 joules. And remember, that's the average kinetic energy of any one of those particles because we don't know how many there are. If we had this number of atoms in that same gas, then all we would have to do is take that energy, 5.81 e to the negative 22, and we would multiply it by the number of atoms that we have. 1 e to the 54, and we wind up with 5.81 e to the 32, and that's the energy of the sample as a whole, right? And so this problem calculates energy per molecule, and then this problem, once we know how many molecules, calculates the total thermal energy of the system. All right, so this idea of heat is an exchange of energy between two objects, just like work is an exchange of energy. We can put work into a system or take work out of a system. We can put heat into a system or take heat out to a system. Heat is always transferred from the most energetic to the least energetic. And I want you to pause the video for a second and think about what does this mean in terms of temperature. And well, we've already talked about hot things having a lot of kinetic energy, and cold things not having a lot of kinetic energy. And so this means that heat naturally flows from hot to cold. A system can increase its thermal energy by either being heated, right, by a flame or a stove, or by having work done on it. And remember, work equals force times distance, and as we drag things a distance, they tend to heat up because of friction. Right? Heat transfer will happen between two objects until those objects reach what we call thermal equilibrium. And in this word equilibrium, you hear the word equal. Right? Always break down those words. And that means that heat transfer will happen between two objects that are in contact until those two objects have equal temperatures, right? So for instance, if I have, let's say, two blocks, and one is at 0 degrees Celsius, which I don't even like that to start. We're going to call that 273 degrees Kelvin, and then we'll call this 373 Kelvin. Right? And if I touch these two objects together, then heat is going to begin to flow between them. They're going to exchange energy until they're equal. And I know that that energy is going to go from hot to cold. And so take a second and think, if I put these things together and they're going to reach equilibrium, some point where those two thermal energies are equal, then what's going to be the final temperature of both of these things? Well, for them to be equal, right, I basically have to divide that heat until both of them are 50 degrees Celsius. Until those temperatures are equal, at which point they do continue to exchange heat. They do continue to exchange energy. However, it's so random that there's a 50-50 chance those things just kind of exchange energy in no net form. They tend to be equal throughout the rest of that exchange. When we talk about heat transfer, if heat is being put into a system, then I define Q as greater than 0. If Q is less than 0, then heat is leaving a system, and if Q equals 0, then there is no net change and that object is in equilibrium. And thermal equilibrium, right? We talked before about equilibrium in terms of forces where there was no net force. This equilibrium is just that there is no net heat gain or loss from that system. And which leads us to our first law of thermodynamics, that the change in thermal energy of a system is equal to the work plus the heat. And so this is kind of an extension of the conservation of energy and conservation laws, right? That if I am doing work on a system, then there's also this heat component that's going to be equal to the change in thermal energy of that system. We can also look at this in terms of the equation for thermal energy, right, is equal to the work times the heat, or I'm sorry, plus the heat going into or out of the system. And remember, if this is positive, then heat is going into the system, and if this is negative, then heat is leaving that system. And so let's take a look at this problem. A system exerts a force of 20 newtons over 0.5 meters over half a meter on an ideal gas. The total change in thermal energy is 500 joules. Is heat transferred into or out of this system? All right, well, so let's see. I've got a force, I've got a force and a distance. So I've got a force and a distance, and I know that work equals force times distance, and so work in this case is going to be 20 times 0.5, which is going to be 10 joules of work done on the system. A system exerts a force on an ideal gas. The total change in thermal energy is 500 joules. So 500 joules is going to be our thermal energy, and that's going to equal our work, 10 joules, plus Q. And I'm trying to figure out if heat is being transferred into or out of the system. So I need to solve for Q. I will subtract 10 on both sides, and I wind up with 490 equals Q, right? That's a positive value, and so what that tells me is that heat is being put into that system. All right, we now have the second law of thermodynamics, and so the first law is simply that work and heat are ways to add energy to a system. We can do them together, but no matter if I do work on a system or if I put heat into or take it out, there's going to be a change in the thermal energy of that system, and we can solve it out accordingly. The second law of thermodynamics talks about this word entropy, right? And the second law of thermodynamics says that the entropy, or the disorder of a system, always increases. And so there's this other really important part, an isolated system. And so remember, this is a system where there are no outside forces acting. And so all this says is that I can't ever really expect my block of ice to do anything except melt naturally and kind of increase the entropy or the disorder of that system. If I take disorder, right, in the state of water, and I create order out of it, ice, then I've got to put work into that system. And that's why we have devices like freezers. This other idea of an isolated system is really interesting because you're saying, well, okay, what about water in the reservoir, freezing in the winter? Well, that's not an isolated system. With that, there's a lot of factors, and it's much, much bigger than just the ice in the reservoir. We're then talking about the whole universe, in which case this doesn't necessarily totally apply. And so this is, for our purposes, we're just going to look at really small systems. What this means for us is that heat irreversibly flows from hot to cold. So when you work out and you generate heat, that heat is essentially lost, right? It's gone. It's irreversible. It'll never come back to your body and be able to do work. And if you heat your body, you're not really able to do a whole lot of work per se with that. This also tells us that a transformation of energy to thermal energy is irreversible. And so when we're talking about our cars taking in joules of gas, but they're only 50% efficient, where does the rest of that go? And that heat is essentially lost. It's never going to come back into the car spontaneously and make that car go forwards. And so these things only make sense for the scale that we're talking about, right? Which brings us to your homework, which I'm sure you'll like because it's pretty short. We're only going to talk about thermal energy and temperature and practice converting between Celsius and Kelvin and using those formulas. And we'll talk a little bit about first law of thermodynamics. I will ask you some conceptual problems about second law of thermodynamics, but not in this homework set. And last but not least, your keyword is Walter, Walter, Walter. All right, I will see you guys tomorrow in class. Have a lovely night.